you can actually see it. Hello, hello. You can actually see it. Let me try reopening VirtualBox here. There we go. You can actually see it's right here, Protostar, and I already have it running. Where you will find that, if you want to use it, is if you literally just go Google search and you go Protostar exploit or exploit exercises. It's probably the first thing that comes up. You can click on that, and then you go to download, and here you can download the ISO file. Now, I'm going to quickly go over, in case you want to practice these on your own, which I highly, highly recommend. It's really great, and you can go through all of them. You would download it from here. I think that's pretty self-explanatory. And then when you're setting up your virtual machine, what I did is I created a new virtual machine. I made it Linux. I made it Ubuntu 32-bit. I'm just going to put something random there for now. I gave it doesn't need really that much memory, or that much RAM, so I just gave it the default value. And then I did not add, this is the thing to note, I did not add a virtual hard disk, so that later on, after I created it, if I go into the settings and I go to storage, I can actually put the ISO that I downloaded here into the disk drive by clicking here. I know that was pretty quick. If you actually want help setting it up, feel free to reach out to me at any point. I might as well put my email in the Slack in case, or not the Slack, in the chat in case anyone has questions about this and wants to reach out to me about setting it up. And then I actually, sorry, I went like this, and then I chose this, yeah. And also, if you ask me for a testing environment in the form that I sent out a while ago, it's also at the end of this PowerPoint. If you didn't know, there was a form right here. If you ask me for a testing environment and I set that up for you, and you want me to put Protostar on there, also reach out to me for that and let me know, and I can put Protostar on there for you if you don't want to go through the work of setting that up yourself. I'm putting my email in the chat right now, so you can reach out to me for that. You can also email CyberHawks, and I'm sure somebody will get back to you, or somebody will forward it to me. Anyway, now that I got through that, really quick, now that I said we're going to be completing these Protostar exercises, I will not be able to go through all of them, that's for sure, in one sitting. If you guys like this and you want more, and enough of you say that you want more, I can continue this for sure. I will ask you towards the end of this presentation if I can keep going through them. If not enough people want another seminar about this, but let's say you're still interested, you can reach out to me individually, and I'd be glad to work on it with you or help you out. However, I learned all this stuff. I know I'm kind of a little bit all over the place today. I learned all this stuff from Live Overflow. It has a terrific binary hacking course where he goes through all of these exercises. And I'm also putting a link to that here. I'll probably put it in the PowerPoint as well after this seminar. But for now, you have it in the chat. He goes through all of the relevant exercises, I should say, because some of them build off of each other. So he doesn't necessarily go through the ones that build off of previous ones, but he goes through ones that are fundamentally different. And his videos are absolutely great. Yeah, that's how I learned this stuff. You won't be able to learn everything from the videos because they're reasonably in depth, but if you don't have all the knowledge required yourself, learning from the video is very difficult. You'll have to do your own research on the side. But there you have that. There are kind of three main types of exploits that I'll be talking about now, at least. The first one is probably the most common one. It's called buffer overflow. If you've ever heard of exploitation, you've probably heard of buffer overflow. So if you look at C, there are functions such as gets that allow a user of a program to write input into a program. However, in higher level programming languages like Python, things like that, or languages like that, usually you don't have to worry so much about buffer overflow because it checks the bounds of how many characters that person can write if they're inputting information, right? But in lower level programming languages, like C, oftentimes programmers fail to check for the bounds. So you can, if you input too many characters, you can end up overwriting other things in the memory. So that's an example of buffer overflow. It doesn't necessarily have to be just input. You'll see we'll have a few different examples of buffer overflows. Like for example, a command line argument that's copied over with string copy or strcpy, I believe it is. If that doesn't check for the bounds, it can overwrite other things. So like if I'm saying if a command line argument is copied to another place in memory, or if anything is copied to another place in memory, that can cause a buffer overflow. A string format exploit is, if you're familiar with printf in C, it allows modifiers like, for example, %f to print a float, or %d to print a decimal, or %d to print an integer, %i to also print an integer. You can use those formats maliciously if the person who wrote the program is not careful, and allows you to, if the person printed out some input that you entered using printf or a similar sort of function, then you can use something like %n to exploit or basically change different locations in memory, or overwrite different locations in memory. And heap, similar to buffer overflow, this actually has been much more difficult to do in recent days because they made a lot of changes to how the heap is laid out. However, there are ways that you can use. I'm not going to go into it in too much detail in this seminar, but there are ways in which you can use the heap to overwrite other locations in memory or other parts of the heap that you're not supposed to have access to if you do it right. So, and if you're curious about how to do any of these things, once again, I put the live overflow link in the chat. Anyway, so that's a brief overview of types of exploits. I know I didn't get too in-depth in them right now. I'll get more in-depth into buffer overflow. Those are the ones I'll be covering in this seminar. A couple things you need to know. We are not going to be worried about these right now. To prevent the sorts of attacks that we are going to be doing today, in modern machines, because what we're using Protostar is to emulate kind of an older machine that does not have these security features in place. Modern machines have ASLR, which is address space layout randomization, and DEP, which is data execution prevention. Now, address space layout randomization, you'll see that when we try to change when we try to overwrite things on the stack and change where control flow goes, meaning change where the program, what code the program executes, we're going to be giving it different addresses that we want it to go to, right? However, without address space layout randomization, those addresses would always be pretty much the same with some minor differences, but we could account for those. However, with address space layout randomization, it gives different addresses every time, so you can't really do that. There's still workarounds for this, but they make it much more difficult. And I will not be covering those in this seminar because that's beyond the scope. This is an intro to exploit development, not a full course in exploit development. Data execution prevention is a measure that prevents you from executing arbitrary code that you wrote if it's not in the right space in memory, or if it looks somehow malicious, if it's not. Mostly if it's not in the right space in memory. So for example, if you had a buffer overflow, this will make more sense when we actually get into looking at a buffer overflow. But if you wrote data to the stack in a buffer, and let's say you put the code that you want to actually execute first in the buffer, and then after that, you overflowed and you overwrote the return pointer that tells the function where to go to once it's done executing, and you told it to go back to the code that you put on the stack. I know that was a lot of words. If you didn't understand that, it's fine. We'll go into that in a second. But let's say you did something like that. Data execution prevention would prevent you from executing the code that you put in the buffer on the stack, because it's not in the code portion of your machine. It's in the actual memory portion of your machine. So, however, the Protostar, which we are going to be working with right now, does not use data execution prevention. There are also workarounds around that, but those are also more advanced and beyond the scope of this seminar. It's really, really important that you understand what the stack looks like, which is why I'm going to be first going over what the stack looks like, at least when a function is called. So I think this is a pretty good diagram that sort of explains it. I also created my own on Notepad. I have a little cheat sheet for myself, but basically this is actually not correct. But basically the first thing you have on your stack, whenever you call a function, the first thing that happens, and I'll make a note to point this out when we're actually looking at code, is it puts the return address on the stack. And hopefully if you if you are familiar with assembly, you know what the stack is. The stack is something that grows upwards and goes back downwards. So stack is first in, last out, I believe, or last in, first out. So when you push something on the stack, you put it on the bottom, and then the next thing you push on the stack goes up, next thing goes up, next thing goes up. And when you pop something off a stack, you start at the top value, go down, go down, go down. Now, if you don't know what a stack is, that was probably a terrible explanation, but hopefully you all know what a stack is. So that was just kind of a reminder of how a stack works. And on a computer, whenever you execute a function, it has to prepare the stack for execution of the function in memory so that everything is laid out correctly so that it can access what it needs to be able to access. And what it needs to be able to access are, first of all, when you call a function, you start from outside the function. You start from somewhere else in memory, and that's going to be what calls the function that you want to execute. So the address of that last instruction in memory before the function that you're going to execute is first stored. It's not really shown here per se. This might not even be the best diagram. Maybe just look at mine. It's stored here. So we have the return address. I'll get to this in a second. So we have the return address, and the return address tells it where to go after we're done executing the function that we want to execute. Where do I go back to in code? What address do I go back to and continue execution from there? After that, we store on the stack what's called the base pointer. The base pointer, I'll get to that later more when we're actually looking at code. But just know that that's the next thing that gets stored onto the stack. Then we have the stack frame, and the stack frame is where your actual variables and arrays and whatever you need to store in memory goes. This is separate from the heap. The heap is another place in memory. So when you do I forget what it's called in C. It's called malloc. So like when you use malloc, for example, in C, to allocate space in memory for something, that's a completely separate space. That's not this. But the reference to that address in memory is stored in here. So all your variables, in other words, are stored in here. But if you have objects, they're stored in the heap. So the heap is a separate space in memory, but all the references to the objects, so like the address of where the object is located, and all the variables are stored in the stack frame. I hope that kind of makes sense. When you execute the program, the first thing it'll do is it'll move the stack pointer. There's a special register that holds where the stack is located, and it will be moved up to create a stack frame that's large enough for all the variables that you need to hold. So that's what happens at the beginning of when you execute a function. It'll move that stack pointer up. So I know I kind of said a lot there. That was a basic introduction to the stack. Also, I hesitated to include this. I had this earlier. This is not entirely true because it kind of depends where the arguments are stored for a function. It really depends on the operating system and the language, how it does it. But generally, a nice way of thinking about it and kind of an easy way of doing it is a lot of the times the arguments are stored before they're stored onto the stack before the function is called. Then when the function is called, it has the arguments here, and it can look here for the arguments, and that's kind of you will see that in some of the examples that we do. So that was a basic introduction to the stack. That's all you really need to know about the stack so far to get started on these exercises. So we're going to get started on the first exercise now. Note that to get to the exercises, once I'm on this page that I showed you earlier, this is the welcome screen, I can go to exercises up here, click on Protostar, and it'll give you a little bit more of an explanation about all the exercises that you have. Notice that you'll be able to log in to the user account with password user. That's pretty important. For some of the later ones, you're trying to access it remotely over a server or server client, which is kind of neat. We won't be getting into those, but for those, you will be able to log in as root with password God mode, as pretending that you are the administrator who is running the malicious code on, or the exploitable code on the Protostar OS, and you as a user will be connecting from it remotely. But we don't have to worry about that. We have to worry about user, password, user. So I'm going to go to stack 0, which is the first challenge that we look at. Now, when I open Protostar, what I actually did is, quick note, I also in the settings, I went to network and I made it, attached it to a host-only adapter. What that means is I can access it from my host machine, so the Windows machine that I'm running this on, but I can't access it from anywhere else. And if I go into Protostar, type a little bit so it shows up. Right now I'm logged in, but if I wasn't logged in, I type in user, hit enter, and then the password is user. I type that in again, hit enter. But now that I'm logged in, I did a basic IPA to find the IP address, or IPADDR, same thing. Note, you can see that I tried if config, but it didn't work. And the IP address, you can't see my cursor right now, but you'll notice that it's 192.168.56.102. So I like to have, I think it's really convenient to have multiple terminal windows open, and I like to use PuTTY for it. So that's why the reason I got the IP address is so that I could connect via SSH here using PuTTY. So now I have two separate terminals that are both accessing my machine. For those of you who use PuTTY, or for those of you who aren't too familiar with PuTTY but would like to use PuTTY, I should say, what I did is I put user at and then the IP address. I can actually load it up here. User at and then the IP address on port 22. I typed in Protostar here. I clicked save to save the session, and now I can open it by double clicking it whenever I want to. So pretty convenient. Now, all of the exercises are located in the opt protostar bin directory. So I'm already there, but if I wasn't there, I could just go cd opt protostar bin, and I'd be there. And you'll notice that we have all the exercises that are mentioned here on the right-hand side in that directory. So now, as a quick note, you'll notice that if I list the information about these, we have you might be familiar with R, W, and X. So this is the user permissions. So this is the permissions for the root user. This is permissions for the owner of the file in the middle. And this is permissions for anyone else. However, the R, I should mention this, the R stands for read, the W stands for write, and then the X stands for execute. I'll get to the S in a second. So what this tells you, if you know about Linux, I apologize that I'm going over this. I just want to make sure everybody understands this because I want to stress this point that I'm about to stress. But what this means is if the R is set for that specific user, that means they're allowed to read the contents of the file. So anyone can read the contents of any of these files. So for example, if I want to see the contents of the file, it's going to look absolutely crazy because it's a compiled binary file, but those are the contents of the file. Yeah. Now, the W means I can actually change the contents of the file. So the root user can change the contents of the file, but nobody else can. So I, as user, cannot change the contents of the file because I do not have that permission. So if I were to, for example, try to edit it in an editor, and I tried to write out with Control-O, it says error writing permission denied. So I cannot write to it. However, I can execute it. That's what the X means. The X is for execute. Now, the interesting part is this S. So this S means that the set UID bit is set. So what that means is if I'm a regular user and I'm executing this, what it'll do is it'll execute it. It'll raise the privileges of this actual program when it's executing. So even though I execute this as a regular user, it will execute it. It will execute and then transfer to root user and then continue execution. That's also why these are in red to tell you that the set UID is there. Now, why is this actually useful? Why would somebody want to do this? Well, for example, you might be familiar with the command sudo. Sudo allows you to run things as a root user whenever you need to, but without having to actually transfer to being the root user. So that, if you'll notice, I might be able to do this really quick. I'm not sure. It's probably user bin sudo. That would make very good sense. If I actually did this, you'll notice that the same thing here, the set UID bit is set on the binary sudo when we execute it. Another useful one is ping. You know, when you want to check if another computer is online, you can ping that computer. Now, the reason, so for example, I can ping this current computer. Now, set UID bit is also set on this one so that it executes with root privileges because it's such a low, doing network transmitting network packets like this is such a low level operation that it just requires root privileges. However, you want any user to be able to see if another computer is online. So that's why it has that set. But that's just kind of a note. Now, the reason I am stressing this so much, that set, is because a very common type of exploitation is, or I should say privilege escalation, is basically making use of this. And if you can somehow exploit this program and you have user privileges, then you can get a shell running with root privileges. So that's why this is so important. Also, there's something called local privilege escalation. That's if you are a user and you have user access to a computer, but you want to have root access, and this is the case that you can, the set UID is there, then you can use this exploit to basically gain root privileges on the machine. Okay, so enough talking. Let's get started. Let's look at challenge 1. So challenge 1 looks like this. You'll notice that we have int modified, we have a character buffer, and modified is set to 0. And then we have a call to gets, which basically just reads input from the user. And then it says if modified does not equal 0, then we'll print you have changed the modified variable. Otherwise, if it does equal 0, we will print try again. Now, you might be looking at this like, well, wait a second, modified is never changed here. So of course, it's always going to print try again, right? Well, actually, no. If you look at gets, if you look at the man page for gets, which I don't really feel like doing right now, because I don't know exactly where it says it, but actually, let's try it just for fun. If I look at the Linux man page for gets with man gets, you'll notice, I did find it right away, it says never use gets, because it is impossible to tell without knowing the data in advance how many characters gets will read. So it basically tells you don't use this because there's potential for a buffer overflow exploit. So what we're going to try to do is the buffer is only 64 characters in length. However, the modified, if we look back at how code is stored in memory, variables are stored in increasing order. So that's why I have this arrow pointing up. So if for each new variable, the first one's going to be stored here, next one's going to be stored here, the next one's going to be stored here. It's increasing, right? So that means that, however, sorry, let me continue with my point there. That means that modified will be stored here first, and then we'll have some amount of space here that's going to be 64 bytes for our buffer. However, the interesting thing is that arrays, the way arrays are stored, like for example in this buffer, is they're written to downwards. So if I write a bunch of, if my buffer is, let's say, this big, if I start writing A's, it'll write them like this. And eventually, if I write too many A's, if I write more than 64, because we only have space for 64, if I write more than that, we'll end up overwriting whatever variables here, which in this case will be the modified variable. And that's the purpose of this exercise. In future exercises, we're going to want to keep overwriting even more until we overwrite the return address, which tells the code where to go after it's done executing the function. And so if we overwrite that, then we can have it go wherever we want it to go and potentially execute some arbitrary code of our own. But for now, we just want to modify this variable. So now let me quickly introduce how to use the debugger in Linux, which is going to be very useful for a lot of these exercises. So the way you use it is it's just gdb is the command, and then you can type which one you want to debug. So we're debugging stack 0. Now looking at this debugger, every program has a main function, right? So you right away know that if you want to look at the code, a good place to start would be to disassemble the main function. Disassemble just means show me the assembly code for this function. So I can type in the forward disassemble, or I can type in disas, and of course I should probably mention that I want to disassemble main. And you'll notice that here's the assembly code for our main function here. And now it kind of depends what format you prefer better. If you prefer MIPS format, this might actually be better for you because you'll notice that for move instructions, you have the source first and the destination second. However, if you prefer, and I prefer CISC format, or Intel, also known as Intel format, it has the opposite. It has the destination first and the source second. The reason I prefer that is because when you're programming and you're creating a variable, you usually have like the destination first and the source second. So you can change the way it looks by I'm forgetting. I think it's set this. Let me use my cheat sheet here. This is why it's nice to have a cheat sheet. Yeah, I was right. Set disassembly flavor Intel. Disassembly flavor until. And now if I disassemble main again, you'll notice that we have the opposite format. So you'll notice that these two are switched around. It also just kind of looks nicer in general. I like this kind of notation for knowing offsets instead of the notation that you see like here, for example. But it just depends on what you're more comfortable with. Either one's fine. Now, to actually run your program, I believe you can type the full word run, but I like to just type R. That's how you run your program. If you want to run your program but pipe input into it, you can use this to pipe input from another file into it. Similarly, you can run with arguments by just typing your arguments in here. So that this would be argument 1, this would be argument 2. If I want to set a breakpoint, I can do that with break, then asterisk, and then where I want the breakpoint to be. So for example, it's useful to have breakpoints before jumps, so we can kind of determine where the code is going during execution. So if I want to have a breakpoint here, I can set the breakpoint here. In PuTTY, I'm right-clicking to copy and also right-click to paste. So when I right-click, it just copies it over. And now I have a breakpoint there. I can also, let's see if we have any other conditional jumps in here. This is an unconditional jump, so I'm not really too worried about that one. We don't have any other conditional jumps, so I'm just going to put breakpoint there. If I run to the breakpoint, or now if I run the program with R, it'll go up to the breakpoint. Of course, first you'll notice that it asks us to input our information. So I'm gonna just input some random A's. And you'll notice that now we hit our breakpoint. It says we hit our breakpoint. From there, if I want to show the registers, I can say info registers. And I can see the values of all the registers here, similar to if you've used Easy68K, similar to that. I can also examine the contents of a register with dollars and then the register name. X just basically means examine. Of course, it told us that the value of it is 0, 0, and then it tried to access the memory at 0, 0, which it cannot read the memory at address 0, 0. But let's say we wanted to read some values off the stack. We could do a similar thing. So if we want to read the top value on the stack, we can do that, right? And this gives us the address, and this gives us the value. If we want to read more information on the stack, we can do x slash, and then let's say however many words we want to read. So let's say I want to read 32 words, right? And then $ZSP. And that gives me the first 32 words starting at the address where the stack is located at. You'll actually notice here that our modified variable is at, and I'll go through this code more fully in a second because I didn't go through it fully yet. But just for now, know that our modified code is, or sorry, our modified variable in our code that remember we set to 0 is at this offset right here. And if I actually examine that, I can kind of see it. I believe it's this one right here, but I can more fully illustrate that point by going like this. You can also add offsets, which is kind of useful. And you'll notice that that is indeed set to 0. So that's kind of a basic introduction to how to use the assembler. Also, another important feature that I should have mentioned is if you started running and you hit a breakpoint, but you want to continue from there, you can just type in the word continue. I believe you can also type in C, but don't quote me on that. Yes, you can type in C. Now you can quote me on that. I just reran the program by pressing R. And if you want to step a single instruction, you have two ways of doing it. You have SI, you have NI. SI follows all of the, is more of a step into, if you're familiar with that kind of terminology. That means that if you have a call to another function, like for example here, it will actually go into that function and then go one by one through the code in that function. However, NI is step over. So instead of following the code that's here, it'll just execute all the code in the call function. Then when it returns, it'll stop again. So those are useful for stepping through instructions. Now that you know how to basically use the GDB assembler, let's get into what this code actually does. So looking at our stack, I'm just going to kind of illustrate the stack down here. So the first thing we do is we push EBP onto the stack. So whatever the value of EBP is, we're going to push it onto the stack. And after that, we're going to move ESP to EBP. So what that does is EBP points to the base of the stack. So it's kind of a reference to where the base of the stack is at any point. So ESP is always going to point to the top of our stack, and EBP is going to point to the base of our stack. So at the beginning of every program, we're taking the old base of the stack from the last function, and we're putting it onto the stack so that when we return, now I'm explaining what the base pointer is kind of, so that when we return to the calling function, we can update EBP accordingly and have the base of the stack of the calling function. I hope that makes sense. Because this currently, what this does is it sets EBP to ESP, because ESP initially starts here. Our stack is initially here, right? So the first thing we do is we push EBP onto the stack so that EBP is, so that our old, the address of our old base of the stack is now on our new stack here. And then, we move ESP to EBP to the EBP register so that now that register holds the new base, the base of our new stack. Let me try to explain again. I don't know why I'm failing with my words today. I'll explain one more time. Hopefully it'll make more sense. If you got it already, sorry. I want to make sure you completely understand this point. So EBP and ESP are registers, right? You can read them here. EBP is always going to store the bottom of the stack. ESP is always going to store the top of the stack. With EBP and ESP is how you access values in the stack. Hopefully that makes sense. Now, because the calling function has its own EBP and ESP, right? So EBP would have the address down here, let's say, in the stack. Let's say this address is whatever. And then ESP is going to have the address of the top of the stack, right? So now that function decides to call our main function, right? So now we have to update EBP and ESP accordingly so that EBP now points to the base of our new stack right here for this specific function, and ESP points to the top of it. However, we have to somehow save this value so we know where to go back to once our function is done executing. So once we're done with our function, which has all its values here, we have to go back to the function that called it. And that it has its values down here, but we have to know what to return EBP to, or what to set it back to when we return to the calling function. That's the reason why we push it on the stack right here. We push the value of EBP onto the stack right here, right? So then at the end of our program, when we call leave, what that's going to do is that's going to set EBP back to this so that it's once again pointing down here. Hopefully that makes better sense now. Now the next thing we have to do is move ESP to EBP, because ESP is currently the top of our calling function stack. However, it's the bottom of the stack that we're going to be using for this function, right? So the function that called this one is using this as their what's known as the stack frame. And we're going to be using this area in memory. However, the top of that calling function's area in memory is the same as the bottom of our current area in memory. So that's why we're setting EBP. We're now setting EBP to point to this. So now both the ESP and EBP point to this location in memory, which is the bottom of our stack. And at this location in memory, currently, at this location of memory, the value of it is the EBP from our previous calling function, so that we know where it should be after we're done executing our function. Hopefully that makes sense. Now, the next thing we need to do, don't worry too much about this line. This line just makes sure the stack pointer is properly the offset is properly aligned. But that's kind of irrelevant. You don't really need to know about that. The next thing we do is we subtract a certain amount from ESP. So notice that here we have low addresses, and here we have high addresses. So the stack grows downwards this way, or the stack grows upwards, I should say, this way towards lower addresses. And if you're familiar with, if you're like, for example, and say if you took EC 242, you're probably familiar with something like move m.l, and then the register values you want to move, and then A7 minus A7, right? And then at the end of your function, you'd have something like move m.l, then you'd have A7 plus, and then the register value that you want to move back. This is literally what we're doing here, literally. So you'll notice that here, when we push stuff to the stack, we're decrementing the address. So it's growing this way, right? But when we're popping stuff or taking it back off of the stack, we increment this way. So we take it from that location, then we increment this way. It's literally exactly the same as that. So we're subtracting a certain offset from ESP, so that now ESP will be pointing to, let's say, somewhere around here. I'll actually put it right up here. And let's say this is, I'm just putting arbitrary values here. And let's say the value is some random bogus data right now, right? So now ESP, in the register ESP, we actually have the value, in this case, x10. Sorry, I made it a greater value. I should have made a lesser value to illustrate the point very well. Yes, because it grows downwards. I made a mistake earlier as well, which is fine. So now this space here is the space we're going to be using to store variables on the stack. Hopefully that makes sense. Now, that's what it does at the beginning. All functions, you're going to notice, have this similar setup at the very beginning. And at the end, you'll also notice a similar thing. You'll have leave and return. Now, if you actually look at what leave does, and I'm not going to bother looking it up, but essentially what it does is move ESP to EBP, and then pop EBP. So you'll notice that the leave is literally just a wrapper instruction for these two instructions. And that is the exact opposite of what we started with. So when we move EBP to ESP, notice that EBP always stored the base of our stack, right? ESP is the top of our stack. EBP is the base of our stack. So by moving the value of EBP, so this hex C, back into ESP, we're essentially moving ESP back down here, so it references this again. Now what that does, that kind of clears our stack. We don't actually have to, we don't have to erase the values from the stack because it doesn't matter. It's just we can leave the bogus data there. As long as we move the stack pointer back here, it's essentially like we're no longer using this memory anymore. So we basically cleared the stack. Then the next thing we do is we pop EBP. So what that means is we take the top value of the stack, we pop it, and we set EBP to that value. So once again, EBP is now going to point to this value. So it's not this one anymore. And that set the stack back to what we needed for the function that called this one. So basically, this here and this here, these are wrappers that set up the stack frame. This between EBP and ESP is known as the stack frame for this current function, and set it up in such a way so that we can restore the stack frame of the calling function when we're done with this one. And return, what that does is right beneath EBP, you will always have the return address. So you'll have the address of the calling function to return to. This is just some random address. And then once you hit this and say return, what it'll do is it'll set EIP, which is the instruction pointer. You may know it as PC or program counter. Program counter and instruction pointer are the same thing. It's just called EIP here, but this is a program counter basically. It'll set it to whatever was underneath, whatever was underneath EBP, and it'll jump to there. So that's how that works. That's if you're really learning how computers work on the lowest level. This is how it works. So now it's time for us, now that you understand that, it's time for us to step through our code. So the first thing that it does, now that we went through all of that, is of course we're pushing EBP onto the stack. So I'm just going to put EBP for now. Note that this is, you know what? I'll do exactly what I did before so you're not confused. So EBP and ESP registers are here. Not yet. Oh, sorry. So we had something like this, right? So let's say this address is OX04, whatever, and it doesn't really matter what the value is. So EBP would currently hold the value X4. We're going to push that onto the stack here, right? So that the stack, which is at address OX02, I don't know, now has that value, right? So that's what this does. It pushes it onto the stack, and it also decrements the stack after doing that. Now, well, actually, it decrements the stack first, I should say. So it moves it up one and then pushes the value there, similarly to what I just showed you with if you used Easy68K and you did the movem.l, you had a minus A7, so it would decrement it first and store the value there. That's what push does. Then move EBPSP. What we basically did is we moved the value, so hex2 into EBP, which means EBP now points here. Now, don't worry about this. This is just so that the offset is correct. Then we subtracted hex 60 from ESP. So now ESP is going to be somewhere here. Of course, my addresses make no sense, so don't pay much attention to my addresses, but you kind of get the point. And then it has some bogus data here. For now, we don't care what it is. Now we actually start our program. So you'll notice that from here, we're moving a word value 00 into ESP plus this offset. Now, if you think about it, since ESP is hex 60, ESP, or sorry, since ESP has been subtracted hex 60, if we take ESP and add hex 5C, we're basically going 1 byte before where it originally was. So we're going 1 byte before here. So we're going to end up right there, let's say, visually representing that. And we're going to set the memory there to whatever this is, whatever this address is. I'm just going to, it doesn't really matter. We're going to set that value to a word 0000, or however many zeros there are. They're actually, this a word value, I believe, is 16 bits here, so whatever. Yeah, and then that's basically what stores the modified variable. So if we go back and look at our code here, when we set modified equal to 0, that's that code right there. Modified is going to be at that offset there, and we just set the value to 0. Now, the next thing we do, let me get my little notepad doc up again, is let's see, what are we doing here? We're taking the address at this offset and we're moving it into EAX. So the LEA, you're probably familiar with LEA if you're familiar with assembly, that's load effective address. So instead of loading the value that's here, so here, notice this was kind of referencing the value. So we put 0, 0 as the value, but here we're taking the address of this and we're moving it into the EAX register, right? So the reason we're doing this is because we're about to call a function. And when we're calling a function, what we want to do is we want to have, in this case, we're calling gets, and what gets needs is it needs the space in memory in which to store the result. And so this is telling it that I want you to store the result here. So it's first moving that address into the EAX, and then it's pushing it onto the stack. So now, let's say this is the address of the beginning of our buffer, right? So our buffer is gonna start here. Actually, I think it's better illustrated like this. So our buffer is gonna start here, let's say. So we have to get the address of the buffer here, and then we're gonna push it onto the stack. So, or we're gonna move it. We're gonna move it there so that then when we call this function, it knows that it wants to store any information into this address here. Hopefully that the general idea, if you don't understand exactly how that works, doesn't make sense, but you should at least understand the general idea. And then once we call gets, it'll modify the memory there with whatever the user inputs. All right. And then the next thing we're doing is here we're testing. So the next part of the code, if you look at the next part of the code, I know I'm going through this really slow, but I want to make sure you really understand how to analyze assembly. In the next, I might do a couple extra examples, but in the next ones I'll go really fast and I won't go through it in detail like this. But here, notice we had an if statement and we checked if modify is not equal to 0. So if you look at the code here, we have, we're taking this, remember, we set this equal to 0 at the beginning. So this was the offset for a modified variable, right? So here, we're taking that modified variable and we're moving it into EAX. And then this test basically tests if it's equal to 0, right? Because it'll set the 0 flag. And if you're familiar with assembly, you probably know what the 0 flag is in the status register. So that sets the 0 flag. Now, if the zero flag is set to 1, so if they are equal, or if EAX does hold the value of 0, then it'll jump to this address, which you'll notice is right here. So it'll skip whatever happens here. Otherwise, it'll continue execution. So this is where we have our first branching of code. Now you'll notice that if it jumps to here, we have a puts call. And the puts call, basically puts is printf on the lowest level. So printf is kind of the wrapper function for puts. And puts just prints out to the console. So we have puts call there. Otherwise, if it doesn't jump and it keeps going this way, then we have a different puts call right here. And then we have an unconditional jump to this address here so that it skips this one. So basically, either if this is 0, it's going to take this jump, move down here, and execute this call and then leave. Or if this is not 0, it will instead continue execution of code. It'll execute this call, and then it'll jump over this other one and leave. So it either executes this call or this call, depending on what we enter. So let's start putting in some random values and looking at the stack. I'm also going to do a nice, I'm going to pull my cheat sheet out for this because I don't always remember how to do it off the top of my head. There's a nice, I guess, cheat, not really cheat, but a nice thing that you can do. You can define a hook stop. And what that means is that whenever you hit a breakpoint, it'll execute a certain commands. And this makes debugging a lot easier because you don't have to keep typing in all the commands every time you hit a breakpoint. You can just say, every time you hit a breakpoint, I want you to execute this set of commands. So I'm going to go define hook stop. And I just want to see, maybe I'll see the next 2 instructions. So I for instruction, at EIP. And once again, EIP is our program counter or our instruction pointer. So I can see the next 2 instructions that I'm about to execute after I hit the breakpoint. And then I'm just going to print the first 32 words on the stack. And then I believe I type in end to finish it. And now whenever I hit a breakpoint, that's what it's going to print out. So let's first run this. I'm going to rerun it. And let's enter in a few A's. Let's actually enter in A, B, 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 C, 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 D, 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 something like that. So we can really clearly see where it is stored on the stack. And now you'll notice that we hit the breakpoint and whatever I defined here in hook stop is what was executed. So if you remember, I put a breakpoint right before this jump. So notice that whatever address you set it as, it'll put the breakpoint right before it, so it won't actually execute the instruction. It'll stop right before it executes it. And what I like to do as a general rule of thumb when I'm debugging is I want to see where control flow goes depending on what sort of input I enter. So that's why I see a conditional jump. Well, that's interesting. It depends on something. So I'm going to put a breakpoint before the conditional jump because then I can see the registers here, like EAX, for example, and see where it goes depending on that. So if we look at the stack, you'll notice that it's in hex, but we entered ASCII. So to figure out where this is in here, we're going to have to convert ASCII to hex so that we know where it is. And to do that, I can just use Python. So I'm going to type in Python, and I can use the CHR to do that. And I'll just type, I think I'm actually doing it opposite. Shoot, I forget how to do this. If I have to reference my cheat sheet, I will feel really dumb, but I might have to do that. I know you can do the opposite, like you can do works for one is A. Sorry guys, I really should know how to do this. It's pretty dumb of me that I don't. This is me being unprepared. Let me look it up. Convert ASCII to hex Python. Let's try this. Hex word A. There we go. Then now we just convert it to hex, and we see that ASCII A is hex 41. Similarly, we can check B, C, and D, but those are just going to be going up one in value. Apologize for the little delay there. And if we actually look for those here, we entered 4 A's, 4 B's, 4 C's, 4 D's. And if you look at the stack, they're actually stored right here. 4 A's, 4 B's, 4 C's, 4 D's. Now notice that, as I mentioned earlier, the array itself grows downwards. So when I entered info, it started at the top, and now it's going down this way. So 4-1, 4-2, 4-3, 4-4, it would keep going this way, right? However, the variables are stored in the opposite order. So the modified variable is right here, and then the actual buffer with room for 64 characters is right here. What that means is that if I write enough A's or enough of any character, I'll eventually be able to overwrite this because it doesn't check that I write. It doesn't check whether the amount of characters that I write is within a certain bounds. So for now, let's just continue. Well, actually, let's, for fun, we know that we're going to jump if EAX is 0. So let's just check what EAX is. Remember, because when we looked at this, we tested EAX first, and then we jumped if it's equal, jump equal, so if it's equal to 0. And you'll notice that EAX is in fact 0. So that means that we will take the jump, hopefully. And so that means that the code we're going to be executing afterwards is this code down here. So it's this call. So if I continue, you'll notice it printed try again. So that means that this right here, this call right here, corresponds to this printf right here. It printed try again. However, what we want to do is we want to change code execution so that instead of going down here, it stays up here, right? And then so it doesn't actually perform this jump. So we can do this manually in GDB if we want to. I'll just enter whatever. It doesn't really matter what I enter. If I believe I can do it like this, set $EAX. Well, we actually already did the test, so I might want to put a breakpoint before the test, so that it has a chance to set the 0 flag accordingly. We're actually going to put a breakpoint there. Break. Now will we run? And now we hit that breakpoint there. And now if I set EAX to some value other than 0, like let's say hex 4, right? And then I can verify that I did that with info registers. Now it's 4. So now when it does the test, it will not set the 0 flag, and it theoretically should not make that jump, and it should execute the other portion of the if statement, which will give us tell us that we have modified the variable. And I hit the next breakpoint, but I'm going to continue. And it says, continuing, you have changed the modified variable. However, we didn't actually change the modified variable. We just went in and edited the register during execution. So you can't really do that if you're trying to break into a program. You won't have access to the assembly and all the registers. You won't be able to debug it. So how do we actually change the modified variable? Well, when we looked at the stack, you'll notice that our A's were stored here. B's were stored here. And all the way up to the modified variable is right here. So as you can probably guess, if I keep writing more information, eventually I'll start overwriting this. So I'm going to do, here's what I'm going to do. I'm going to rerun this program. I only want my second breakpoint, not my first one. So I'm going to delete breakpoints and I'm just going to put this one back. Okay. I'm going to enter a ridiculously long string and see where this gets overwritten. So we're going to go A, B, 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 C, 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 D, 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 D. Now, the reason I'm doing groups of 4 is you'll notice it looks really pretty when I print out each word, because each word is 4 characters in length. So you'll notice 41414141 is AAAA. So if I want to know exactly where the offset is, I can just print 4 of each. Now, hopefully that'll be enough to get us an idea of where it is. Now, if I do that, you'll notice that what was a 0 before is now hex 515151. And if we want to figure out what character that is, you'll notice that that happened at Q. So we don't need to overwrite these. Notice here we're overwriting the base pointer and then the return address. As I talked about, if you look at the stack, underneath here you have the base pointer, and then here you would actually have the return address. I didn't mention that. The calling function should have pushed the return address there. But we don't need to overwrite those. We just need to overwrite the modified variable. So we only need to go up to Q to actually overwrite it. So that's what we're going to do. We're going to rerun it. I'm just going to copy and paste this to save time. And then if I continue, you'll notice it says you have changed the modified variable, because you'll notice that we did overwrite it, but we didn't overwrite anything after, because we didn't need to overwrite anything after. Now this is how we did it. Notice that we did it within GDB, but now we could actually do the exact same thing without being in GDB. So I can actually copy and paste this. Actually, it's on separate lines, so that might not work out too well for me. But if I quit out from GDB and I just try to execute stack 0, and I copy this ridiculously long string, and I enter that, you'll notice that we have successfully changed the modified variable. So that's a basic exploit. Now, that took me a lot longer to explain than I expected. I don't know why I thought I'd be able to get through all the stack exercises. But since I wasn't able to get through the later ones like I wanted to, I wanted to show you on this one something that might be convenient for future ones that get more complicated. Another way of testing this, for example, is, or I should say another way of exploiting is to write a Python script. So for this one, for example, we entered all these characters. I don't know why it's doing that. There we go. We entered all these characters, which took a while to type them all out, right? But once we know, this is pretty long. This is a pretty long command. But once we know how many of these characters we need, we can use Python to simplify this process by quite a bit. So I'm going to use Python to print all these characters out. I'm going to use Python -c, which allows us to execute Python code inline. And I'm going to use print. I'm just going to print out A. And now I don't even have to print out all these different letters. I can just print out A that many times and it'll still overwrite the modified variable. Now I just have to figure out how many times I want to print it. So you'll notice that we print each letter 4 times. So I'm going to put 4 there, and I'm going to multiply it by the number of letters there are, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yes, I think I counted that right. So 4 times 17, we're going to print A that many times. So now you'll notice if I just execute this, it'll just print that many A's. And you'll notice it's the same length as what we had here. However, I can pipe the output of this function into the input of stack 0, which is the function we're trying to execute. And if I do that, it's basically going to run stack 0, and it's going to take the output of this and put it in there, kind of like what we did manually, but it'll do it all in one line. And boom, you have changed the modified variable. So that's how you do a Python inline. You can also write Python code if you want to. Like, for example, I could go nano exploit.py. And then from there, I can say, I could do a very similar sort of thing. And I can go Python exploit.py, and I can pipe the output of that. Now I'm just running the script, but the script is essentially doing the same thing as this one line here. I literally just copied this code from here. Now I can run that on. Pipe the output to this, and similarly, we have, again, been able to change the modified variable. Another thing I can do is I can take this, and I can output it to a file. Let's say I'll call this input, because this is going to be input to here. And then if I run this, I can redirect the contents of the file to there, and I should get the same result. Yeah. So a lot of different options on how you can do this, and depending on what sort of exploit you're working with or what sort of exploit you're writing, different options will be more convenient or less convenient. Especially with the later ones, where you have a lot of padding, and then you want to enter an address or something. This is going to be really convenient. Now, because I ran out of time, and I'm already well over time, I'm just going to explain some of the concepts that I wanted to demonstrate, but I'm not actually going to demonstrate them. But if you look at, if we keep going through these exercises, this one's pretty much the same as the last one. However, it uses string copy and it copies the first argument. So rather than entering input, you're copying an argument. So it's literally exactly the same thing, except instead of entering all those characters and piping them in, this time you are taking you are entering them in as an argument. So I can actually do this one real quick, just for the sake of demonstrating this. And the next thing you'll notice that's a little bit different is now it checks if modified. Instead of just checking if it's different, it's a little bit more difficult to challenge. It checks if it's this specific hex value. So what am I doing? Not that. So to figure out, once again, to figure out what character this is, I can go Python, and I'm just going to copy it. I'm just going to go like this, OX61. That looks like lowercase a, 62, etc. I can tell it's ABCD. So instead of the cues that we inputted earlier, which were 51515151, I'm going to input ABCD. Other than that, it's going to be exactly the same. Now, this brings me to the difference between big endian and little endian machines. This is a big endian machines would store it in order. However, little endian machines store it in reverse order for each word. They store each character in the word in reverse order rather than in order. So instead of ABCD, I would have to put in DCBA, and then when it actually reads it, it'll read it in the reverse order. I know I kind of brushed over the concept, but essentially here's what I can do. In Python, this time I'm gonna, because I want the last four to be ABCD, right? I'm only gonna do this 16 times so that it only prints up to here, and then the last four I can change to whatever I want to change them to. Then I'm going to go DCBA. I'm going to add DCBA to the end of that. So if I just print this, you'll notice that we have this, but it ends in DCBA. And now to do this as an argument, to execute a command and pipe that in as an argument, or not pipe that in, but put that in as an argument, I can use backticks to do that. And so now if I do stack1, and I put that as the argument, it says you have correctly got the variable to the right value. So that's how you solve the second challenge. This one's kind of the same as well, except first of all, it's instead copying an environment variable rather than an argument. So instead of an argument, I'm going to have an environment variable that I set here, and then I'll set the value of it here, similarly with Python, and then I'll execute the challenge immediately after. And notice that instead of this hex is kind of weird. You can't actually convert it to ASCII. If I tried to convert it to ASCII, it would be a strange value. Yeah, it's like \n. So what we're going to have to do is we're going to have to actually enter it in as hex using Python. And the way I would do that is instead of, if I write in Python, if I write print ABCD, instead of writing actual values like that, I would do \x and then the hex value that I want. And because this is a little endian machine, I would make it OA, OD, OA, OD, right? And then I'd add that to the end of this. And then I'd do what I showed you earlier where I put that in as the environment variable value, but I'm not actually going to do that because no time. This one is interesting. This executes a function pointer, and we are attempting to execute the win function. So it's similar to what we've done before, except we have to find the address of the win function, which we can do in GDB using examine, just like we examined registers. We can also examine. Okay. We can also examine the location of functions in memory. So this is stack 3. If I examine win, you'll notice that it tells me the address of where win is located at. That's right here. And this is actually the first instruction of win. So if I did x win, you can actually see that this instruction corresponds to this hex, but this is the location. So instead of overwriting with DCBA or with values like we did in the last one, we're going to have to actually overwrite it with the address. And a useful way of doing that in Python is I can import struct, and I can write my addresses like this. We want to pack it as an integer, and I can put whatever the address is, whatever. I'm going to write some bogus for now, and I don't have to worry about little endian or big endian because the Python struct function will automatically take care of that and move these around as necessary. So it might put in this order, it might put this, or might put this, then this, then this, right? It might put in reverse order, it might put in the same order. But then after that, I can just print, save this to a variable, and then I can print that out, right? So that's kind of useful. And then similarly, I'd print my excessive amount of A's, however many A's I need. I'm just putting in a random value for now, and then I'd add this address at the end of it. So that's how you'd solve that one. This one's interesting because unlike the last one, it doesn't give you, actually it does give you a function change. However, it doesn't execute a function pointer, so you can't just overwrite a function pointer. This time you have to overwrite the return address, which basically means you have to figure out the offset required to, instead of going down to like here, for example, you actually have to go lower to below the base pointer to where the return address is, which the return address is going to be somewhere here, right? And then you have to actually overwrite that so that when the function tries to return, it ends up going to the win function instead of down there. I feel like there was something important to note about that. Oh, really quick way of doing that is you don't even have to open GDB. If you want to figure out the offset, all you have to do is opt protostar bin stack 4. Let's see. Actually, I'll GDB it. And now, if I run and go a b b b b c c c c d d d d e f g h I j, oops. You'll notice that we receive a segmentation fault. That means it tried to execute memory, or it tried to execute an instruction at memory that was invalid. And we can actually see where it's seg faulted. So it tried to return to this address and tried to execute an instruction there, but there were no instructions there. So that's why it did a seg fault, and it tells us exactly what address it failed at. And that's 54545454. So we can really quickly figure out that that is, I think I have 2 GDBs running, that is where our T's were. So I actually entered just enough characters to do it. And then we'd end up putting the address of the win function, which we get once again from going like this. We'd put this where the T's are supposed to be. And we can do that using Python, using the \x, or using struct.pack like I just previously showed you. So that's that one. I'm literally just going to go through the rest of the stack ones and call it a day. This one's more interesting because it wants you to run your own shellcode and get a root shell. So this is like a full-on exploit. This is how you actually get a shell on a remote computer. And if you go on to the exploit database, which we're going to be looking at on Wednesday, if you attend my exploitation seminar, you'll see code that basically takes advantage of these buffer overflows, and then they have their own shellcode that they execute afterwards. And what we'll be doing is we'll be modifying the shellcode that is executed so we can get whatever type of shell we want. So shellcode is basically just computer code on the lowest level. And what we want to do is we want to get shellcode that executes bin sh, right? Because bin sh basically gives us a shell, and if we can get this one to give us a shell, then we've essentially got root privileges on the machine. We've got a shell. So what I did is I found the operating system. You can go on Shellstorm, has a lot of really good shellcode for different uses. And I just found shellcode that somebody else wrote. Actually, I don't think I used this one. I think I used a different one, but I could use this one. Here you see bin sh. And then here we have the actual hex shellcode for it. So I would just copy this and I'd paste it into a Python program. And I'd actually put that, I'd put that in somewhere inside the buffer. Before we actually overwrite the return address, we're going to put it in there, and then we're going to change the return address to point to the beginning of our shellcode. I'm not really going to go in depth about that or explain that super well, but essentially, hopefully that made sense that the return address is going to point to somewhere inside the buffer earlier where I put a shellcode, and our shellcode is going to spawn a root shell. I also should have mentioned this earlier. I went through all these exploit exercises myself. And if you go to my GitHub page, which I can put a link for in the chat. I'm almost done, guys, I promise. I know this is ridiculously long, and I know nobody's here now, but somebody will be watching the video later. And they might watch this, they might want to see this. So I have all my solutions to all these exercises. So if you're ever curious and you don't know what to do, you'll notice that here's my script for this one. You'll notice that here I have the address of where I'm jumping to in the buffer. Here I have the shellcode, which is also called the payload. I also did something called, so the actual location of the stack changes a little bit depending on what environment you're executing it in, so it's not always going to be the exact same address. So what you do is you create a bunch of, you put a bunch of NOP instructions or no operation instructions. And then what those do is they basically say do nothing and go to the next instruction. And the reason that that's useful is that I can put a bunch of these, like a ton of these, and then I can put this afterwards. And then if I cause the return pointer, or if I cause the instruction pointer to go back to somewhere in the middle of this slide, right? It doesn't matter exactly where in the middle, then it'll run down the slide and eventually execute this. And now if the address is slightly different in a different environment, then it doesn't matter, because either way it's going to hit somewhere inside it's going to hit one of these NOP instructions. It doesn't matter which one. It might hit one earlier, hit one later, but either way it's going to go all the way down, continue executing those, which basically they tell it to do nothing. So it'll just keep moving on to the next one until it hits our shellcode. That's known as a NOP slide. It's a NOP slide because it slides down, keeps executing no operation instructions until it hits the shellcode. That's that one. Yeah, I can actually, I don't think it's worth my time demonstrating this, but if I copy this, I can actually demonstrate that I get a root shell. I don't know what I did here. All right. Huh, interesting. So stat6 looks kind of different. This one is similar, but it doesn't actually allow us to execute code that is on the stack. It checks to make sure it's not on the stack. If it is on the stack, it's just going to exit. So what we actually have to do here is, there are a couple different methods. There's return to libc or return-oriented programming. You know what? This is getting ridiculously long anyway, so I'll just call it a day there. I think I explained enough. If you're interested in learning more, please shoot me an email. I'll say it just in case you're watching this video later and you don't have it in the chat. It's jford11@hawk.iit.edu. You can also email CyberHawks on their email. And if I have enough interest to keep going through these, I will gladly make another seminar on them. If there's not enough interest, but one person or two people, let's say, want to keep going through these, then I'd be glad to meet with them individually and keep going through these. But basically, that is what exploitation looks like on the lowest level. And on Wednesday, in our exploitation tutorial, in the exploitation seminar, what I'll be doing is I'll be taking code that somebody else created for us, because here we're creating the code kind of ourselves. But I'll be taking code that other people created for us, and we're literally just going to be changing the payload portion or the shellcode to be what we want it to be, so that we can have a shell or like either a reverse TCP connection or a bind TCP connection to the computer, and then executing those exploits. So yeah, a lot of information. But I guess that'll be it, and I'll call it a day. I can also put a link. I'll put a link to the live Overflow videos in case anybody wants them somewhere in this PowerPoint. But I'll do that after I end the recording of the seminar. That's it. Thank you for those of you who did watch part of it. I know I went overtime, so probably everybody left because I went well overtime. But thank you for those of you who came. Thank you for those of you who are watching this afterwards. If you ever have any questions, feel free to reach out to me. My name is John Ford. I'm presenting this on behalf of CyberHawks. And yeah, that's it. Let me just stress, if you are still interested in receiving cybersecurity information as well as a test environment to practice in, and you haven't filled out this form already, it's at the end of the PowerPoint. Yeah, that's it. Thanks for watching. Thank you to David for